Okay, so this is going to be an example problem. No, there's an F on there. This is going to be an example problem looking at forces on current carrying wires, what they do, and how it relates to torque and the rotation, all that stuff we just talked about in the mini lecture on the same topic. So here is our example. We have a magnetic field, uniform magnetic field of 0.25 Tesla. We have this square loop inside that field. Each side of that square is 0.32 meters long, and the current in each of those sides is 12 amps. So what is going to be the force in each one of these sides? What's that force going to result in? You might guess it's a rotation. And then what's the torque? If it is in fact a rotation, which let's hope it turns out to be. All right, then what's the torque? So let's look at this problem. We're going to look at each one of the sides individually to get that net force acting on this loop. We're going to remember that the force on a current carrying wire is the current times the length. Wrong equation. Let me start that over. The current times the length times the field times the sine of the angle. So that's going to be the relationship that we remember. Let's first look at the force on side A. And what do we notice right away about that force on that side A? Well, it's parallel to the magnetic field lines. It's as if those charges are just walking along the white line on a highway, right? They don't feel any force. So the force is going to be zero. You can also put in sine of 0 or sine of 180 in that, in this case 0, but in that would be also give you the sine of, both those values are 0. Okay, so there's no force in A. What about the force of B? Well, the force on B, that is in a direction that has a perpendicular component to the magnetic field. In fact, it's 90 degrees, so we get the current times the length times the field. The sine of 90 is 1, so we're at a maximum force here. And when we calculate that all out, we get 0.96 newtons. And what is the direction? Well, I'm always cautious about doing the right hand rule in front of you because it looks like my left hand. But if you do that right hand rule, you put your fingers in the direction of the current across the top. You curl up the direction of the field, and your thumb should be pointing back at you. So that tells you it is out of the page. All right. C, well, C is similar to A, and it's just 180 degrees, but it is, in fact, parallel to that magnetic field, and so we're not going to feel a force in that part of the loop. And force D, well, that again is perpendicular. We have the current times the length times the magnetic field. The fact that it's perpendicular gives us that maximum strength, so the sine is 90 is 1. So we again get 0.96 newtons, and the direction, you might suspect it's the other direction, so it's going to be into the page. But please do that right hand rule to practice it. So now we have a force out of the page on one side and into the page on the other, so it's feeling a force like this. Well, like this, I guess, in the orientation that it is. So it's going to rotate. It's going to rotate, which means it must be experiencing a torque. So let's calculate that torque based on our torque relationship. So when we think about our torque relationship, let's remember that the torque relationship is mu cross B. And mu, remember, is N times the current times the area times B times the sine of the angle, where that angle is between mu and B, or between the surface area and the the magnetic field. So the arrow perpendicular to the surface area and the magnetic field. So in our example here, mu, that area that is going to be out of the page, okay, perpendicular to that is out of the page. It could also be in the page. We're just going to call it out of the page. And the sine of the angle of B, so they are perpendicular to one another at 90 degrees, and that 90 degrees. We're not going to worry about the direction. I'm trying to think if that was said wrong. It doesn't matter. 90 degrees is what we want to focus on. So it's going to be at a maximum. The number of loops we have, well, it's just one. Our current is 12. Our area is 0.32 squared. Our field is 0.25. And we get a torque of 0.3072 Newton meters. All right, so that torque is 3.72. We know it's going to rotate in this direction, so it's actually rotating in the, I guess if I look down, it's going to be in the clockwise direction, the clockwise direction if we look from the top down. Okay, so we can get a torque, we can get forces, right? And recognize that means it's going to rotate. So what happens here? Let's say it does rotate, starts to rotate. When does it stop rotating? Well, it's going to stop rotating when the mu is parallel to the magnetic field. When the moment direction and the magnetic field direction are parallel. When does that happen? Well, we have to kind of look at that from a different perspective, okay? Because it's hard to visualize that when this is going to be when things are in and out of the page and all of that. So I'm just going to I'm going to take this and I'm just going to rotate it all in a different orientation so we can explore that, what that would really kind of look like from a force perspective, as well as from a torque perspective, what it just visually looks like. I'm going to get rid of all this stuff just to avoid that just as a distraction. All right, so if we imagine that our electric field, let's look at it as if it's going out of the page, into the page. And I have a current carrying wire like this. So in this orientation, what would we see about the forces? Now, every wire now is experiencing a force. The forces on the outer edges, on the right and left edges, well, again, if you put your fingers in the direction of the current, you curl into the direction of the force. This edge experiences a force in this direction. This edge experiences a force in this direction. Similarly, this edge is going to experience a force in that direction, and the bottom is going to experience a force in the downward direction. And now, my net force on that loop is 0. There's no force on that loop. Similarly, is there a torque? Well, as soon as I rotate this, or as soon as this is rotated in this orientation, here's my area. So the vector perpendicular to that area is in line with the magnetic field. So the torque is also equal to zero. So when this loop rotates, we get a situation where the torque, the forces go to 0 and the torque becomes 0. And then no more rotation happens. And how can we use that to our advantage? Well, if I put a loop in a magnetic field, it's going to rotate until the moment vector is parallel to the magnetic field vector. If I turn the current on to remember, current has to exist, charges have to be moving. I turn the current on in this loop, and it begins to rotate. Before it aligns, I turn the current off. Now, that current carrying wire does not feel an electric force, a magnetic force, because charges are no longer moving. But the wire has started moving itself. And so in the absence of a force, it's going to or a torque, it's going to continue to rotate. That's Newton's second law. Or first law. Good grief. That's Newton's first law. So it continues to rotate. And then I turn the current back on. And it feels that force again, rotating again. And if I time it so that rotation causes it to continue always to feel the force in the same direction, to feel the torque in the same direction, I can continue to get this to rotate and rotate by adding current on, current off, current on, current off, current on, current off. So I can use it like a motor. I can get it to spin just by adding current in brief dosages inside a magnetic field, so inside of a magnet. All right, so it's kind of a fun way to think about kind of how motors work, one type of motor, in that idea of using current and its influence by a magnetic field. All right, good job.